Hello everyone. Today we're going to present our Capstone project on repackaged Android app detection. This project is inspired by Lee, Bisande, and Klein's paper in 2018. The instructor is Professor Kaiser and the mentor is current PhD candidate in computer science, Shi Singh. Due to the openness and freedom of Android platform, repackaging of Android apps has become one of the most serious threats to the whole Android ecosystem, as it deprives app developers of their benefits, contributes to the spread of malware on millions of Android devices, and increases the workload of market maintainers. Usually, repackaged Android apps come with a mixture of benign and malicious code, which makes the detection very difficult. In this project, our goal is to build up models that can distinguish repackaged apps from their original counterparts by utilizing a combination of static code analysis and behavioral analysis of the apps. We hope that our contributions will forward the process of repackaged app detection, spark innovative approaches going beyond the current state of the art. For more background of our project, Android apps can easily be reverse engineered, modified, and released again to the market, since anyone with adequate tools can have access to the source code. This graph demonstrates how reverse engineering happens. Basically, the malicious app developers take the legitimate apps, repackage them with harmful codes, and put the new apps into the third-party app stores. Then whoever uses the apps will have a series of information leaks and potential loss in treasure. Our data came from the popular Android Zoo repository. It contains pairs of proof repackaged apps with original apps stored in hash values. Then, based on this dataset, 15,297 repackaged apps were collected with the corresponding pair 2,776 original apps.
After having access to the dataset, we designed a complete pipeline to get the data we need for our following experiments. First, we downloaded the data into Android package files and decompiled these APK files to Java source code. Secondly, the team members utilized REX and DFS to extract the sensors, features, and permissions usages from source code. Lastly, we stored this data in multiple CSV and JSON files. Then we conducted some exploratory analysis and got the following results shown in this slide. For instance, among all the repackaged apps, 804 of them use additional sensors than their original counterparts. We also performed data visualization to better showcase our observations and findings. Some plots on sensors, features, and permission usages can be seen in the next two slides, and you can refer to our report for more graphs. One drawback of our dataset is the imbalance of it, as we have more than 5 times more repackaged apps than original ones. Since we consider malware detection as a classification problem, the imbalanced nature of our dataset could lead to inaccurate results while training. We have tried 4 ways of manipulating the datasets, including downsampling, random oversampling, duplicating original apps based on pair information, and SMOT. Since the dataset is imbalanced, we use balanced accuracy score and ROC-AUC score as our major evaluation indicators.
In terms of modeling on sensor, feature, and permission dataset, we applied several sophisticated classification models, including logistic regression, SVM, KNN, random forest, XGBoost, and multi-layer perception. Moreover, among the 4 ways that we mentioned in the last slide to solve the imbalance of the data, we eventually choose random oversampling and SMOT to test and compare results, since these 2 methods make more sense in our case. After running all the models on 2 preprocessed datasets that we mentioned, we compared our results and picked the top 3 models that gave the highest scores. We can see in the left the ROC curve of our models in 2 different oversampling scenarios. For the first oversampling method, random forest achieves the best balanced accuracy score, which is 0.7. For the SMOT method, the result is relatively low and the best balanced accuracy score is 0.68. Now we consider the random forest as our best model, since it gets the good balanced accuracy score in both methods. We visualize the 10 most important features and we can see that the ability to access Wi-Fi is the top important features in our best model.
After analyzing the sensor data, we focused on the flow data of 804 pairs of apps, which are significantly different in the Jakarta similarity. In this case, control flow graph and data flow graph are applied to measure the change in contents from different directions. A control flow graph is the graphical representation of computation during the execution of programs or applications. It is mostly used in the static analysis and compiler applications, as they can accurately represent the flow inside the program unit. This method was originally developed by Francis E. Allen. We use the AndroGuard extension, which will read through each APK and create a directional call graph from each APK. On the other hand, the data flow analysis is automatically enumerating the data flows inside the program. All components are based on the Suite compiler optimization framework, which is responsible for converting Java bytecode into GIMPO intermediate representation. Unlike many other static analysis approaches for Android, we use the FlowDroid, which aims for analysis with very high recall and precision. Here is an example of tint analysis in a data flow graph. If the source of the value of the object X is untrustworthy, we say that X is tinted. To tint user data is to insert some kind of the tag or label for each object of the user data. The tag allows us to track the influence of the tinted object along with the execution of the program.
The main dataset we focus on is the 804 APK pairs, which the repackaged APKs utilized extra sensors. We extract the flow path through the sensor in each app and also added a CFG analyst for the additional 7,000 pairs with the same sensors. The selected models are similar to those before, except we also add gradient boosting. To deal with imbalanced data, we use random oversampling and duplicate original by pairs. Again, balance accuracy is also our main evaluation indicators. Focusing on 804 APK pairs, we can see that the total performance of the models in CFG only is much better than the models in DFG only. Neural network and gradient boosting perform pretty well among all the models of CFG. In DFG, SVM and logistic regression perform better. Combining CFG and DFG together, the performance does not change much compared with the models in CFG only, except KNN. However, adding all 7,000 pairs with the same sensors, the models on CFG performs worse because the control flow is passing through each sensor node in the graph, and the majority of the datasets has the similar sensor information. Since gradient boosting performance is relatively better in the datasets of 804 pairs, we also analyzing the feature importance. The control flow paths from full screen activity to sensor managers and the data flow graph construction time are much significant in these models. So this is a brief summary of what we have done throughout the semester. We utilize different methods analyzing sensor information between repackaged and original Android apps. We hope that our works can help push the areas of Android app detection further and inspire new ideas and experiment in the future. We also truly appreciate the help from our advisors and mentors and wouldn't be able to complete this project without their help. That's all of our presentation, and thank you for listening.